We're going to look at tree diagrams today, and I can't say enough about these. I've had situations in the past where I've been confronted with a problem that I didn't know how to do, and so that I was unfamiliar with, and so I tried a tree diagram, and it just made it so clear that it was easy to solve after that. So these are really handy. And first I want to talk about, what if you were to toss two coins? Whoops, that's supposed to say two coins, and you wanted to look at the different probabilities. So the way you would set that up on a tree diagram is you would first do the first toss. And of course there's only two outcomes, heads or tails. And then the next column is going to be the second toss. And you could get heads or tails again for either one of these. And so this is how you would set that up. And then on the branches themselves, you put the probability. So you have a half a chance of getting each one of these. You have a half a chance of every single one of these as well. And then you can see all the outcomes. Tree diagrams show you everything. And to get all the outcomes, you run along the branches. So heads, heads is one of them. Heads, tails, tails, heads, and tails, tails. And then to get the probability of getting heads and heads, you use the multiplication principle, 1/2 times 1/2. The probability of getting the first head times the probability of getting the second head. Heads, tails. See, all of these are going to be 1/2 times 1/2. So they're all going to be 1/4. And then you can see that the chance of getting two heads is a fourth, the chance of getting two tails is a fourth, and the chance of getting a heads and a tails is actually a half. And then that all adds up to 1. So when you multiply along these branches and then add them all up, you should get a total of 1, because you're including everything. That'll take us to this first example. Carl's car will only start 80% of the time, and his motorbike will start 60% of the time. We're going to draw a tree diagram to represent all the different possibilities. So in the first row, the first column I mean, we're going to do the car. And then in the second one, we'll do the motorbike. I'll just call it a bike. So the car's either going to start or it's not going to start. You could do S, I'll just say not start, NS. And then the bike is either going to start or not start. Same here. Whoops, that's supposed to be an S. I don't know what my deal is today. The car is going to start 80% of the time. So you can put 0.8. That means 20% of the time it won't start. The bike is going to start 60% of the time, so 40% of the time it will not start, and that's going to be true here and here as well. And so then you can see there's going to be 4 different outcomes. There's the 4 of these branches that you can follow. On letter B, I, both will start. Find the chance that both will start. So that means that the bike will start and the car will start. That's this branch right here, SS. So the 0.8 times 0.6 will give you the probability that they both start. So that's going to be 0.48. Almost 50% of the time, he's going to be good to go either way. Second question, Carl can only use his car. So that means that if he can only use his car, then what happened to his bike? Well, it didn't start. So this means that the car will start and his bike will not start. So that's going to be car starting and bike not starting. It's going to be this branch right here, 0.8 times 0.4. That's and so that's 0.32 or 32% of the time. Wow, we're already on this one. Okay, example 12. 2 boxes each contain 6 plants that have yet to flower. Box A has 2 plants that will have purple flowers and 4 that will have white. Box B contains 5 that will have purple and 1 that will have white. A box is selected by tossing a coin and choosing a plant. Determine the probability it will have purple flowers. So you either have box A or B. That's your first choice. So this is the box, A or B. And if you choose box A, the plants are either going to, and it's helpful if you label these too. The plants are either going to have purple or white. Same with blue. I mean, in box B, they also have purple and white flowers. So that's the setup there. And then how are we choosing box A and B? We're tossing a coin. So we have a half a chance 50-50 chance of getting A and B, so you put your halves on there. And then I have to read this. So there are 6, box 8, 2 out of 6 will have purple. And I'm kind of looking at this. Sometimes it's good to leave these unreduced, because then everything will have the same denominator. So the 4, 6, 4 of them will be white. And let's see, the blue, I have to step back, contains 5 that will have purple. Add a 6, and 1 will be white. See, the 1 6 isn't going to reduce, so I'm going to just leave them in sixths and see what happens. Determine the probability it will have purple flowers. So that means that could either come from box A or B, so we have to consider a couple of branches here. We have to consider, and I can highlight. I love it. Let's do yellow. So this branch would have purple flowers, and this branch will have purple flowers. So I could have, and then you just multiply along the branches. 1/2 times 2/6 plus 1/2 times 5/6. And I'm glad I didn't reduce these fractions, because now I'm going to have a common denominator, because I'm going to be adding these. So that's going to be 2/12. You don't want to cancel these 2's, because you want the common denominator. Plus 5/12 is 7/12. All right. Fun. I love these. I hope you guys do too. I always say that, don't I? Next section, G. This is going to be sampling with and without replacement. And on these problems, you can use a tree diagram, or you can choose not to. Sampling with and without replacement actually is done in real life to some extent. In factories, when they're manufacturing things, they have to do quality control, so they have to take random samples and make sure that things are being made correctly. And sometimes when they're sampling, once they sample it, they can't put it back. Like if you're going to sample chocolates, for instance. You're not going to be putting those back. But on this first one, we're going to do replacement, so we are able to put them back after we sample them. Maybe it's an electronics part or something. Sampling, so we've got a box containing 3 reds, 2 blues, and 1 yellow marble. Find the probability of getting 2 different colors if replacement occurs. So there's all kinds of possibilities. You can think about each one and write them all out. I'm going to do a tree diagram, and of course I love tree diagrams. And then you can see, you make sure you don't miss any that way too. So, okay, I'm looking here, 2. So we're going to have 2 choices. So first we're going to choose a marble, and it could be either red, blue, or yellow. So there's 3 red, blue, yellow, 3 possibilities. And then we're going to choose again. We could also get red, blue, or yellow. Now notice replacement is occurring, so that means we're starting back with the original marbles every time. So we will down here be able to draw yellow again. Even though there's only 1, we're replacing it, so it's still possible it's there again. Then when we do non-replacement, this won't be here. And then you put your probabilities on here. There's 3 out of 6, 2 out of 6, 1 out of 6. I'm not going to reduce these. You can choose to if you want, but I kind of like to leave them so I get common denominators. And then we're replacing, so these probabilities are going to be identical on all these branches. And now, it's pretty nice. I'm going to get my highlighter out again. And I'm going to highlight all the ones that have 2 different colors. So red, blue, red, yellow, blue, red, blue, yellow, yellow, red, and yellow, blue. I've got 6 different branches I need to multiply. So I've got 3/6 times 2/6 plus, and oh, by the way, we're going to be adding all of these up, because you multiply along branches, and then when you get all the different branches, you add them up together to get the total probability. So now I've got 3/6 times 1/6 plus 2/6 times 3/6 plus 2/6 times 1/6 plus 1/6 times 3/6 plus 1/6 times 2/6. And then I'll go along, and I know my common denominator is going to be 36. So I'm going to have 6 plus 3 plus 6 plus 2 plus 3 plus 2. 22/36. That wasn't too bad. Divide by 2, and we get 11/18 as our probability. Of course, I'd like to check and make sure I got the same thing when I did it by hand. By myself, yes. Great. Now on the next one, we're going to also have 3 reds, 2 blues, 1 yellow. 3 reds, 2 blues, 1 yellow. But this time, we're not replacing. So again, at the beginning, we still have on the first draw, this is the first draw, we could have red, blue, yellow. Now on the second draw, we could also have red, blue, and yellow, because there's enough. Red, blue, yellow. And then down here, we don't have another yellow, so we just have red and blue this time. So you have to be watching there. Probabilities on the first one are going to be the same, 3 out of 6, 2 out of 6, 1 out of 6. But on this next one, we've chosen a red, so there's only 2 out of 5 left. Blue, there's still 2 out of 5, and yellow, there's 1 out of 5. First one, we've chosen a blue, so there's still 3 out of 5 left there. There's only 1 out of 5, and there's still 1 out of 5. On the yellow, we have 3 out of 5 reds and 2 out of 5 blues left to choose from. Okay, back to my highlighter. Again, we're doing the same thing. Oh, I already forgot the question. What was it? Getting 2 different colors. Okay, 2 different colors. So we've got red, blue, red, yellow, blue, red, blue, yellow, and these are different. Now, one thing I'm noticing, again, I have those 6 branches, but notice there's only 2 branches that are not included. I'm going to use the complementary events, the idea of the complementary events. Instead of finding these 6 probabilities, I'm going to find these 2 probabilities and subtract them from 1. So I'm doing 1 minus the probability of getting a red, red, plus the probability of getting a blue, blue, because it's impossible to get a yellow, yellow. I'm going to, again, not reduce, so red, red is 3/6 times 2/5, and a blue, blue is 2/6 times 1/5. So that's going to be 6 plus 2 is 8 over 30. That's what, 22/30ths, and so we divide by 2 and we get 11/15ths. Pretty cool, huh? Complementary events are very, very handy. They save you time. Number 14. A bag contains 5 reds and 3 blues. 2 are drawn simultaneously. Determine the probability that at least 1 is red. When things are drawn simultaneously, is that replacement or non-replacement? Well, it has to be non-replacement, because if you have 2 at a time, then the first one in your hand has already been chosen when you're pulling that second one. I know you're doing them both at once, but this is a case of non-replacement. And so you have to keep that in mind. Now on this one, I'm going to do it without a tree diagram. And I'm going to think about this a little bit. The probability at least 1 is red. That means you could have red, blue, blue, red, or red, red, right? So the choices are red, 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 blue, blue, red, and blue, blue. Those are the only possible ways of doing this, right? And notice the first 3 all have a red in them. So instead of finding these 3 probabilities, I could find the probability that there are no reds and subtract that from 1. 1 minus the probability of no reds would be the same as the probability of at least 1 red. So in other words, I'm doing 1 minus the probability of a blue, blue. And that I can just think about easily enough. 1 minus. The chance of getting, so blue, blue, the chance of the first marble is blue is going to be 3 out of, there's a total of 8 here, 3 out of 8. And then the second one, this first blue has already been chosen, so there's 2 left out of 7 remaining. And so it's as simple as that. 1 minus 6 over 56, that's going to be 50 over 56. Divide by 2, I've got 25 over 28 for my probability. remember those complementary events. They really do save you time. Oh, are we done? We are done. Wow.